According to the established scientific knowledge, the concept of propellantless drive is impossible because it violates Newton's third law, and, consequently, the principle of conservation of momentum at the center of mass of the system. As a result, the concept can only be worked as a science fiction exercise to explore basic insights that, eventually, could be validated by the scientific community. One preferred approach to the propellantless drive starts with the oscillatory motions that result from the unbalanced rotation. Forced vibrations of a mechanical system are the most important in applied mechanics, and a particular case is that of unbalanced electric motors. In this case, the mass of the motor is subjected to a periodic force F of magnitude omega F. The forced circular frequency of the motion is the angular velocity of the motor. This force can be an external force applied on the mass of the motor, or, according to the established knowledge, a centrifugal force produced by the rotation of an unbalanced part of the system. After the appropriate operations, the equation for the amplitude of the vibration is According to the established knowledge, the force produced by the rotating unbalanced armature is the centrifugal force. M, the mass of the rotating armature, times R, the radius of rotation of its center of mass, times omega, the rotational speed squared, which causes the displacement of the motor from its equilibrium position. There are two problems with this argument. First, since the motor is displaced from its equilibrium position by a distance given by equation B, the action of a real force is required. However, the centrifugal force is not real, but fictitious. The second problem with this approach is that the motor is considered a single body, with an unbalanced rotating part. These arguments make the process incompatible with Newton's third law. To solve this problem, it is needed, first, to consider the motor, when running, a system of two bodies in inertial conflict. The first, the stator under restriction, whose center of mass coincides with the axis of rotation. And the second, the unbalanced armature, whose center of mass is located at a distance from the axis of rotation. The moving center of mass of the armature tends to move in a straight path, thereby causing the acceleration of the stator. The stator resists acceleration, and this resistance acts upon the armature, causing the path of its center of mass to curve. The center of mass of the armature manifests inertial resistance to move in a curved path, and this resistance acts upon the stator continuously. This allows the identification of the action-reaction pair, making the displacement of the unbalanced motor in accordance with Newton's third law. An oscillator can be built, joining two equal electric motors, with symmetric counter-rotating unbalanced armatures. The oscillation remains constrained to the vertical direction. Considering the situation where the oscillations are in phase with the driving force, that is, when the force is oriented upwards, the motor is above the equilibrium position. It is noted that the motion of the center of mass of the system results only from its internal dynamics. Starting from this observation, the aim of all mechanical devices, developed over the past 100 years, is to work with a fixed angle toward the preferred direction of motion, avoiding the backward motion that characterizes the oscillation. 4 devices have proved successful in demonstrating this possibility. The main task in this video is to consider the main features of a device concept, comprising 2 unbalanced interconnected bodies, which rotates through the angle of rotation of less than 90 degrees, followed by rebounds at the 2 sides of the angle to reverse the directions of rotation. The study model consists of a first body, arm-shaped, whose center of mass is located close to its front end, opposite to the interconnection of the 2 bodies, and a second body with center of mass closer to the interconnection, which is also the rotation center of the 2 bodies. Rebound springs are fixed to the second body, defining the angle of rotation, when they collide with the first body, to reverse the directions of rotation. It is proposed an arc electric motor to maintain the opposite rotations of the two bodies, with its primary fixed, preferably to the first body. The feasibility of this device configuration depends primarily on the forces produced during rebounds at the sides of the rotation angle, particularly in the expansion of the springs, in order to avoid backward pulses that would make the system an oscillator. When the first body strikes the spring, the two bodies stop momentarily, with the spring compressed, and then are accelerated with the spring expansion. The ideal situation would be one in which the resultant of forces on the interconnection is zero during the expansion of the spring. When the spring starts expanding, it applies a pair of equal and opposite forces on the bodies, which begin to move. Their centers of mass move with a tendency to follow a straight path, according to Newton's first law. Supposing that the resultant of forces on the interconnection is zero, the moving bodies, due to their asymmetry, cannot follow their straight paths at the same time. The first body pulls the second body forward so that its own center of mass can follow its straight path. The second body resists this acceleration and pulls the first body backwards so that its center of mass can follow its own straight path. As a result, the inertial tendencies of the bodies are counteracted, causing opposite accelerations, allowing to confirm that the process is in accordance with Newton's third law. The process is cyclic, and the expected forward motion takes place in pulses. With a configuration employing just one pair of counter-rotating bodies, however, this ideal condition does not happen. The spring force, acting upon the second body, produces a backward resultant on the interconnection. To neutralize it, a forward force, with equal magnitude, should be produced by the first body, acting upon the interconnection. This force depends on the velocity of the first body, which starts to move from rest when the spring is compressed. When the spring starts to expand and applies maximum force on the second body, the velocity of the first body is just increasing from zero. In the short time of the spring expansion, a resultant backward force acts upon the interconnection, causing a backward pulse on the system. This backward motion can only be neutralized when the first body is moving at maximum velocity. The backward resultant decreases with the spring expansion. When this backward motion is stopped, when the first body moves through the angle bisector, the first body can pull the system forward. The forces produced by the expanding spring on the two bodies are as follows. First, the spring force acts upon the second body at a distance from its center of mass. As a result, it causes the second body to move in a general plane motion. That is, the center of mass of the body starts moving parallel to the force, and the body rotates about the center of mass, in this case, counterclockwise. Two forces act upon the interconnection. The first is a force equal and parallel to the spring force, and the other is a force tangential to the circle the interconnection moves, around the center of mass of the body. These forces compose a backward resultant. Simultaneously, an equal and opposite spring force, acting upon the first body, causes its opposite rotation about the interconnection. Since the spring force is applied between the center of mass of the first body and the interconnection, a force is applied on the interconnection, but whose magnitude is less than the applied force. The first body starts to move, so that its center of mass manifests a tendency to move in a straight path. The backward resultant of the second body acts on the interconnection, and, consequently, on the center of mass of the first body, as a centripetal force, which curves its path backwards. The center of mass of the first body resists, and this resistance acts upon the interconnection as a force, here being called centripetal resistance. Since this resistance depends on the velocity of the center of mass of the first body, it has a magnitude less than the backward resultant. As a result, during the spring expansion, the resultant of forces on the interconnection is not zero, as would be desired. Under the action of the backwards resultant, the interconnection moves in a backward curved path. When the spring expansion is complete, the first body is at maximum velocity, which means that its resistance to the backward incurvation of its path is maximum. This centripetal resistance acts upon the interconnection and stops its backward motion. When this is achieved, the system is pulled forward by the centripetal resistance manifested by the center of mass of the first body. When the first body strikes the opposite rebound spring to end the cycle, the system has moved a short distance forward. The forward motion of the second body is obtained due to the inertial resistance of the first body to move in a backward curved path. In accordance with Newton's third law, during the interaction process, implying Newton's third law, the center of mass of the system moves forward because the first body transfers kinetic energy to the second body, as described in other videos. In conclusion, this model, consisting of only one pair of counter-rotating bodies, is potentially capable of moving forward, but with less efficiency than it would be if the first body could start already at maximum velocity, which cannot be the case. To avoid the disadvantage resulting from the use of only one pair of counter-rotating bodies, an alternative is to employ two synchronized pairs, with the motion of the second pair delayed in relation to the first pair, to maintain one pair lagged behind the other. In addition to a gearbox, electronic control means for the arc electric motors could be used while one pair is rebounding to reverse the direction of rotation. The other pair is moving through the angle bisector, cancelling the backward resultant produced by the first pair during its spring expansion. This device concept is described as a study model to illustrate the interpretation of Newton's third law in the curvilinear motion. If this interpretation is accepted in the future, it could encourage the design and development of viable electromechanical systems for satellite maneuvering.